Welcome everyone to Friday Office Hours. We're really excited to have you today and happy Friday. We have a presentation today about some of the electronic health records and wearable data. So before we get started though, I do have a little bit of housekeeping. This presentation will be recorded. So I've hit the record button and we are on our way with that. And then I do have one quick announcement about a new feature coming to the or launched to the User Support Hub. So we recently launched earlier this week community for all of us researchers on the User Support Hub. And really this is a place where you can go and you can share tips for using the Workbench, work with other researchers, find collaborators on research projects. To participate in the community, you will just go to the User Support Hub and using your researchallofus.org credentials, you can actually log into the User Support Hub and access that. That QR code will lead you straight to community on the User Support Hub. And of course, there are some guidelines and policies related to that you will see and be able to interact with. If you have any questions though, please do let us know. I'm going to now introduce our presenter for today, Dr. Evan Brittain. Dr. Brittain is a professor of medicine in the Division of Cardiovascular Medicine, co-director of Vanderbilt Pulmonary Circulation Center, and associate director of the Vanderbilt Coordinating Center. He received his medical degree from Cornell Medical College and completed internal medicine residency and cardiology fellowship at Vanderbilt. During fellowship, he received advanced training in cardiovascular imaging and clinical investigation through Vanderbilt MSCI program. His translational research program focuses on identifying mechanisms of pulmonary vascular disease and right heart failure using experimental models, clinical trials, and epidemiologic methods. His work also leverages wearable devices to monitor and promote physical activity in pulmonary hypertension and other chronic diseases. He has received funding from the NIH, FDA, and American Heart Association. He treats patients with heart failure with preserved ejection fraction and directs the inpatient cardiology consult service at Vanderbilt University Medical Center. And now it is my pleasure to stop sharing and hand the reins over to Dr. Brittain to talk a little bit about research in the All of Us research program that he's been a part of.
Wonderful. Thank you, Anna, for the introduction. Can you see my slides okay?
We can. They look great.
Excellent. Okay. Good afternoon, everyone. Thank you to the organizers for the opportunity to share some of our work. So I'm going to be talking to you about sort of this novel integration of commercial wearable devices with the EHR, and I'll try to convince you that there's clinical value in doing in integrating these data streams. So a little background. This crowd may be familiar, but just in case, a little background on a simplified version of how the data are managed in All of Us and where the wearables come in. So when participants are consented, they're invited to fill out surveys, share EHR, physical measurements, etc. And there is also a wearable tech arm, which in the current phase of the data available is what's called bring your own device. So this is patients who already own their own device and agree to share their Fitbit data with their EHR. So these data are entered into a repository. They're curated by the Data Research Center, and they're made available to investigators on the Research Hub. And that's a cloud-based platform where the data stay there, they're analyzed there, et cetera. And so I'll start with the question of why we would want to link wearables in the EHR. And I'll try to demonstrate the clinical value, but I think it's also important to consider that these data are important to our patients. And that's evident by the fact that there's about 100 million Americans who have some kind of activity tracker on their wrist, and that's about a 1 in 3 of the U.S. population. And interestingly, in a recent study, almost all of these individuals, 83%, would be willing to share those data with their treating physician. Another reason from a provider standpoint is that it's easy to imagine that risk profiles differ based on someone's behavior. So these are examples of 4 individuals, step counts on the y-axis, 4 years of time on the x-axis. who have very different behaviors. So these individuals have low step counts. These individuals have high step counts. And I think it's easy to imagine that these individuals have very different risk factors and chronic conditions compared to these individuals. But in patient care today, we don't have this information on a day-to-day basis. This is more representative of patient care today, where we get these snapshots of information over time. So this is an individual patient's electronic health record spanning about 4 years. And what you see is each one of these dots is some kind of condition that was coded, a medication, a lab value that was collected. And so we have a lot of information about an individual during this time period. And then there are spans that last a year or more where we really have no information at all about how that patient is doing. And so the premise here is that knowledge of behavior during these intervening periods could allow us to make better medical decisions on an individual basis. So I'll show you some of the projects that we've done, really just trying to learn what we can from the integration of wearables in the EHR. The design of this is all retrospective. It's all observational. The data that are available include some curated Fitbit data, which I'll describe, and then anything that shows up in an EHR. So ICD codes, vitals, labs, and survey data. And again, these are individuals who already owned a Fitbit and agreed to link their activity data with their EHR. So one of the initial challenges is dealing with these high dimensional data is, because you've got minute level step counts and heart rate data. And so trying to tease out the signal from the noise. And so we made some semi-arbitrary exclusions where we were trying to really identify patients who wear their devices regularly so that we could enrich for some compliance. So, for example, we excluded days where the wear time was fewer than 10 hours per day. We excluded days where there were extreme ends of the tails in terms of steps per day. Excluded data that was collected when an individual was under 18 years old. And then we also excluded months where we thought that the habitual wear time was too low to be valid. And so we excluded months where they had fewer than 15 valid days. And that culminated in about 15% of total months. And then I'll show you some sleep data as well. And here we excluded individuals who had fewer than 4 hours of sleep on greater than 30% of days. Again, sort of arbitrary, but in the service of trying to get habitual users so that we would have a real sense of what their behavior was. So this is a flow diagram. The numbers you're going to see here will vary from study to study because these data are being made available over time and more patients are added to the cohort. So the absolute numbers here are less important than the flow. So at the time, there were around 200,000 individuals with EHR data. About 6,500 of those individuals had a device and agreed to link it to their EHR. We further enriched for compliance, as I described in the last slide. And then we were really concerned about this idea of reverse causation. So it's possible that people have a condition because they walk fewer, they're less active. And it's also possible that they're less active because they have a chronic condition that impairs their ability to be active. And so one way, you really can't eliminate that concern in retrospective data, but one way we tried to mitigate it was we ignored any diagnosis that was made during the first 6 months of monitoring under the assumption that that condition probably already existed but hadn't been clinically recognized yet. And so imperfect, but some effort to mitigate this concern about reverse causation. So these data are already out of date, but at the time there were 14.3 million person days of monitoring, 139 billion total steps, and almost 7 million sleeps. And I say sleep instead of night because there were also some shift workers who slept during the day. So again, the numbers are less important than some of the proportions. So roughly 7,000 individuals, sort of early middle age. And then some of the important things to keep in mind as you interpret these data is that the vast majority were white. the vast majority were female, and the vast majority were college educated. And so this really just reflects the consumer who goes out and buys a Fitbit and agrees to wear it. So some clear diversity issues in this particular data set that are already been addressed by the All of Us program. So coming in a later collection of data that's going to be available maybe later this year, there are data from individuals who were provided a Fitbit, and that's a much more diverse population. So some of these issues will be remedied. So it's important to note that the people who own Fitbits are different from the people who don't, and are different from the rest of the All of Us cohort. So for example, the rest of the All of Us cohort is much more diverse, much more sex balanced, and also more balanced in terms of education. And if you look at the health parameters across pretty much every organ system, not surprisingly, the individuals who wear the Fitbits tend to be healthier. The Fitbit data that are available extend back to when the Fitbit account was created rather than when they were enrolled in All of Us. And so as a result, there really is very long-term monitoring available. So the median monitoring period for this cohort was around 4.5 years. And in many individuals, we had 5, 6, 7, 8 years of monitoring. So we know a lot about the behavior of these patients. This is the distribution of step counts in thousands. On the left, median step count was around 7,000. And then on the right is fairly active minutes, which the Fitbit algorithm is proprietary, so we don't have full information, but this is thought to be equivalent to what the CDC and the American Heart Association consider moderate intensity activity, which is what the public health activity guidelines are based on. So the median fairly active minutes is around 9 in this cohort. So I'm going to tell you, describe a few projects we've done. So tell you 3 stories. The first one is physical activity across the human phenome. And a starting off point, I think, is this sort of cultural notion that 10,000 steps is the optimal target for good health. And what we found was 10,000 really wasn't necessary. Fewer steps than that were associated with good health. And I think that there's some interesting background about where that 10,000 number came from. The most plausible story that I've read is it comes from the wake of the 1964 Olympics, which were held in Tokyo. There was a surge of enthusiasm for exercise after the Olympics, and one of the local clockmakers took advantage of that and began to sell a personal pedometer, and it was called the Manpo-K meter, which means 10,000 steps system. And the story goes that 10,000 was chosen because the character for 10,000, if you squint, looks a little bit like a person walking. And so I don't know if that's the true story or not, but that's sort of the best dots connecting that I've seen. And so I'm just going to show you a few studies linking step counts with activity, and the story is really consistent. So step counts on the x-axis, events on the y-axis, lower is better. And what you see is as step counts go up, the adverse events go down. So no surprise, really consistent across lots of different studies. But I think one of the challenges with interpreting these data is that they use a very short monitoring period. So patients were given an actigraph or other device, and monitored for somewhere around 7 days, send the device back, and then they're followed for years with no information, behavioral information in the intervening period, and then they're assessed for an outcome. So you can imagine there's some challenges to interpreting what someone does when they're being monitored for 3 to 7 days, and extrapolating that behavior over years to an association with an outcome down the road. And so that, I think, is one of the unique advantages of the All of Us cohort, is that we've got 4.5 years on average monitoring duration for these individuals. So we wanted to look at the association between step counts in this case and human health. And we wanted to do that really in an agnostic, unbiased way. And so we did what's called a phenome-wide association study. And I'll describe that methodology a little bit. So you're maybe more familiar with a genome-wide association study. And in this design, you take a disease, COPD, heart failure, for example, and you look across cases and controls across the entire genome, and you arrive at the potentially variants that are associated with this condition. So FIWAS sort of inverts that. So here you're starting with a variant or a lab value, or in this case, an average daily step count, and you're inserting that's the input, and you're looking across a broad range of phenotypes, in this case, everything that shows up in an electronic medical record. And you're looking for diseases that are associated with your input, in this case, step counts. And so this was our initial FIWAS. We used average daily steps. Again, we excluded any new diagnosis within the first 6 months. And the effect size that you'll see is for every 1,000 step increase, minimally adjusted here for age, sex, and race. And we did this across 1,700 fee codes. Excuse me. So fee codes are really just collapsed ICD codes. So to give you an example, there are probably about 10 ICD codes for coronary artery disease. But in the end, they all mean that the patient has coronary artery disease. So you can collapse those down into a single fee code. And that reduces some of the multiple comparisons challenges with using high dimensional data. So I'll walk you through this figure. So the y-axis is the p-value. The x-axis is the odds ratio. This is a logistic regression. Protection in this direction by increasing steps, risk in this direction. And because it's a multiple comparisons issue, we used a Bonferroni adjustment. So that's this line here. So everything north of this line and in this quadrant is associated with reduced risk as step counts increase. And not any major surprises. So sleep apnea, obesity, diabetes. But we're some new and interesting observations around mental health, gastroesophageal reflux disease, et cetera. So we took this collection of diagnoses and we removed diagnoses that had just a few patients. We removed non-specific conditions like nausea and vomiting or shortness of breath, which are a little challenging to interpret. And we removed acute conditions because we're really interested in what happens over time. And so we were left with this collection of diagnoses. And here you can see the effect sizes a little bit more clearly. So for example, for every 1,000 step increase that's observed, the risk of obesity goes down by about 11%. And we carry these forward into some Cox models that are now fully adjusted. And one of the important things that we were able to adjust for is step counts over time. And so this accounts for behavior that changes over time on an individual level. So hazard ratio on the y-axis, average daily step count in thousands on the x-axis. And what you see is that risk for most of these conditions begins to emerge at around 8,000 or 9,000 steps, below 8,000 or 9,000 steps, I should say. And so in general, there were mostly linear relationships where more steps means more protection. But there were some interesting nonlinear associations, particularly here, diabetes and hypertension. You can see there seems to be sort of a ceiling effect at around 8,000 or 9,000 steps per day. So this was interesting because we think it's sort of an initial step toward being able to personalize and put a threshold on where risk begins for individual conditions. The second story is around sleep. The sleep data were released not too long ago, and so we wanted to understand if there were clinical value in sleep data from commercial wearable devices. Sleep is gaining sort of importance culturally. This is a recent addition from the American Heart Association to other behaviors that are associated with good cardiovascular health. And so sleep was recently added to that list. So the data that I'm going to show you are in contrast to a lot of the sleep literature, which is based on either self-report or a single night of polysomnography or actigraphy data that doesn't stage sleep. And so really there's a paucity of continuous longitudinal sleep data. And I recognize fully that Fitbit-derived sleep data are imperfect compared to somnograms or research-grade devices. But I think the density of these data and the longitudinal aspect are of value. So here I just want to highlight a few things about the cohort. Again, same issues with demographics, mostly white females who are college educated. On this column here, this is the average duration of sleep in hours. And you see that females sleep a little bit longer than males. White individuals sleep about 45 minutes longer than black, self-reported black individuals. The average sleep time is around 6 hours and 45 minutes, 15 to 20 minutes of restless time during that. And then here are the sleep stages by percent of time spent in a given stage. So about 21% of time in REM, mostly light sleep, which is expected, and then about 15% in Fitbit-derived deep sleep stage. This is a heat map of all the 6.8 million sleeps that we observed. So sleep duration in hours is on the y-axis. Sleep onset time is on the x-axis. And the more dense the red, the more common that combination was. So the median sleep onset time, I have to say I was pretty surprised by this, was 11:10 p.m. And in fact, 75% of the sleeps we observed had an onset time at 10:30 or later. We also observed some naps and what we think are shift workers, which will be interested for future studies. So I'll walk you through how we went about. Again, we did this in sort of an unbiased way. We didn't want to go into it with a preconceived notion about what conditions sleep would be associated with. So we looked across the entire human spectrum of human disease. So this is, again, that PHIWAS methodology. The y-axis here is p-value. The horizontal line is, again, that multiple comparison adjusted p-value. And here it's organized by organ system on the x-axis. So what we found was average sleep duration really didn't have a ton of associations, obesity and sleep apnea. Reassuringly, as restless sleep increased, there was more likely to be a diagnosis of insomnia or sleep disorder. So that was sort of an internal reassuring control. This was probably one of the more striking findings, and I think probably the most clinically actionable as well, is we looked at sleep regularity or variability. And we defined that by using the standard deviation of sleep duration. So for example, if you slept roughly 7 hours every night, your standard deviation would be very narrow. If you slept 5 hours one night, 10 hours another night, that's a very wide standard deviation. And what we found is that as the sleep irregularity increased, that was associated with numerous conditions, and importantly, across the entire spectrum of human disease. So lots of different organ systems affected by sleep irregularity. And I think that's clinically actionable because it's hard for me to counsel my patients and say, get more REM sleep or get more deep sleep. But it's relatively easier to say, look, you need to go to bed at roughly the same time each night and wake up at roughly the same time in the morning. And that's associated with better health. We did all the stages and a bunch of other metrics that I won't go into here, but just wanted to highlight one association with rapid eye movement sleep is as that percent of REM sleep went down, the risk of atrial flutter and atrial fibrillation and other arrhythmias went up. And this is actually something that's been observed in observational data from self-report and appears to be borne out here as well. And so it suggests that sleep hygiene could be a lever for intervention in some of these rhythm disorders. We also observed some interesting J-shaped associations where too little sleep and too much sleep are both detrimental. That was mostly for these mood disorders and hypertension. And just to give you a sense of sort of quantifying this, so for example, if you sleep 4 hours, the risk of major depression disorder more than doubles. And similarly, if you sleep 10 hours, the risk of depression more than doubles. So some of the takeaways here is that high variability may be one of the most detrimental sleep patterns and also the most modifiable, as I discussed. Atrial fibrillation in sleep stages, I think, warrants further study. And most sleep guidelines and recommendations suggest 7 to 9 hours of sleep for adults. But what we observed is that many patients were perfectly healthy when they averaged 7 hours of sleep per day. So that may be sort of the middle of the healthy range rather than the floor. And then, I think we found some insight that commercial devices may provide some important and actionable information about sleep hygiene that we can leverage in the clinic. And then the final story I'll tell you is trying to answer the question: how much physical activity is needed to mitigate the genetic risk of obesity? So I think it's intuitive that the lower your activity, the higher the risk of obesity. And it's also intuitive that genetic risk for obesity probably varies across individuals. And so we're trying to combine those two concepts and quantify physical activity needs based on an individual's genetic background. So here we're combining clinical data from the EHR, behavioral data from the Fitbit, and genomic data from the more than 200,000 genome sequences that are available in all of us. And so when you look at the overlapping number of those individuals, there are about 3,100 individuals. And unfortunately, we were limited by power to those of European descent. This number was much smaller for the other races. And so we're very interested in seeing if this validates in other races, but this was really restricted to those of European ancestry. So I don't want to go over this completely, but what we did here is we developed or calculated a polygenic risk score for body mass index. So we used all the genetic sequencing data that were available, and we used large-scale publicly available GWAS data of prior BMI studies, and we calculated a polygenic risk, and we separated here individuals into quartiles. So the quartile 1 had the lowest polygenic risk, quartile 4 has the highest. And just want to point out a couple of data points here. So all of these individuals were not obese at baseline. That was by study design. But the risk of developing obesity over the course of the study went from 13% in the lowest quartile to 43% in the highest quartile. So this is sort of an internal validation that the polygenic risk for BMI was doing what we expected it to do by identifying higher and lower risk for obesity. This is our full model, and what I really just want to point, this is a Cox model hazard ratio on the y-axis, or on the x-axis rather. What I really just want to point out is that both average daily steps and polygenic risk were independently associated with the risk of obesity. So they're giving us complementary but different information. So I'll walk you through the way that we modeled this. So here we have a Cox model for obesity adjusted for all the variables I showed you on the prior slide. The hazard ratio for incident obesity is on the y-axis. Average daily step counts in thousands on the x-axis. And we stratified this by polygenic risk score percentile. And so, for example, this middle curve is someone who's at the 50th percentile for genetic risk. And this yellow curve is 75th percentile, and then the first curve is 25th percentile. And if you assumed, so the median polygenic risk percentile, that individual would have to walk around 8,700 steps per day to reduce the risk of obesity. And if you assumed that was the target for everyone, you would underestimate the risk for the 75th percentile. So for example, if everyone in the 75th percentile walked 8,700 steps per day, their risk of obesity would actually go up by 33% over time. Another way to model that is to look at how many steps are needed across polygenic risk percentiles. And so for example, again, 50th percentile was around 8,700. But if you're in the 75th percentile, you'd have to walk 11,000 steps per day. So about 2,200 more steps per day compared to an individual who's at the 50th percentile. And so one of the important takeaways here is that you may be able to personalize activity recommendations by accounting for someone's genetic background. And it also suggests that public health recommendations that are one size fits all may underestimate the amount of activity someone needs to reduce, in this case, obesity in individuals who have high genetic risk. And so you might imagine a future where activity recommendations incorporate genetic background as well. Here we looked at, it depends on where you start. So we looked at baseline BMI and the number of steps needed to reduce the risk of obesity, depending on where you are on that spectrum of polygenic risk. And so each one of these point estimates, each one of these dots is a hazard ratio of 1. And so, for example, someone who is at the 50th percentile of polygenic risk and started at a BMI of 24 would need to walk around 7,500 steps per day to achieve a hazard ratio of 1. And contrast that with someone who starts at a BMI of 26, again, same polygenic risk, they would need to walk closer to 12,000 steps per day to reduce their risk. And so it matters where you started at baseline in terms of your BMI. So those are a few of the projects that we've done, and I've tried to sort of highlight the limitations of despite being a very high value, some of the limitations of this cohort. So there's selection bias around who is in this cohort because it required you to own a Fitbit. It only used Fitbits, and we realized that there's variability across vendors in terms of what counts as a step or an active minute or a minute of sleep. And I think there's potential within all of us to expand that to HealthKit, incorporating Apple data. I talked about the potential for reverse causation. You can never really eliminate that in retrospective studies, but we did our best to mitigate that concern, and certainly we'll be testing those associations in prospective studies. And then EHR data inherently have some limitations around what gets coded, how often patients see their providers, what tests get ordered, et cetera. And so keep that in mind. So some conclusions. I've tried to convince you that these devices provide both clinically valuable and actionable information about disease risk. I was struck that sleep irregularity seemed to be one of the most important drivers of poor health. Genetics and behavior modify obesity risk in ways that are not captured by public health recommendations, and perhaps that could be remedied in the future. And then I think these data in general make an argument in favor of integrating wearable devices with the EHR that might in the future enable both evidence-based and personalized behavior recommendations. So in there, lots of people to thank who actually did this work, particularly Jeff, who was a programmer and generated virtually all the analyses you saw, and Haral Master, who's in the Data Research Center at Vanderbilt for all of us and has been a tremendous resource. And Paul Harris, who's the PI of the Data Research Center, has been a great supporter. And much of the sleep data was generated in collaboration with experts and collaborators from Google, who we're thankful for. And I'll be happy to address any questions.